I'll take it off. Welcome everybody to Phius Alliance Chicago. What month is this? April. It's the merry month of April. And it was a beautiful spring day, and I hope you people were out enjoying it to some extent. So I'm Tom Bassett Dilley, and I'm joined by Al Mitchell of Phius, and we're going to talk about retrofits. And we want there to be plenty of conversation. If you have any questions or comments that are productive, or things that we should know about, etc. And we're going to focus mostly that on the end. But while we're going, if there's something important that you'd like to chip in about, please do. This will have CEUs. You got to stick around to the end where we have the number on the CEU slide at the end. And so anyway, yeah, it's going to be the Phius Revive update and sort of the Retrofit Summit recap. I'm going to be running like 5 case studies and talking about those, but Al is going to take it away first to talk about what is the Revive standard.
Great. Thanks, Tom. Yeah, so this is going to be a briefer summary of what we talked a little bit about at the Retrofit Summit. And like Tom said, please ask questions, dump them in the chat, unmute yourself and say something. So Phius has been trying to respond to this retrofit conundrum. There's thousands and thousands of homes, especially within the area that a lot of you serve, that are in dire need of retrofits. And some people have said, yeah, I want to retrofit to full passive, but that's just a little too hard, or it's a little too far. It's out of the budget because they're still paying off the house or something like that. Or I'm concerned about the embodied carbon of it. So we've been working on developing a new retrofit standard to try and respond to those concerns. And I'd like to show you a little bit of the visioning and then some of our early testing. For a full timeline, the whole document of the standard will probably be coming out for public comment mid or late May this year. And then with the proposed launch either later this year or January 1st or something like that. So we're trying to build in a lot of the things that people benefit from passive buildings. So decarbonization, the thermal resilience, the health, and the quality assurance, but into a different calculation protocol and a different means of getting to that point. And it's our belief that every building should support the health of the people. So is it providing you adequate shelter? That's the number one life necessity that a lot of our buildings provide us. And then is it benefiting is it either not inhibiting your health, like older homes with poor air quality or mold issues or any of that? We want to make sure none of that's happening, or maybe the building can benefit your health. And then there's maintaining the livability of the planet for mankind. So that's related to the decarbonization front and the reduction in emissions. So resilience plus health plus decarbonization are the big 3 points that we're trying to hit with this new standard. And to detail that a little bit more, the resilience is not just the thermal resilience, which is the main resilience bit that I've been working on in the research going up to this point, but also that determines your insulation and your air sealing. But are you building the home in a floodplain? And if it is it well protected against that flood? Are you susceptible to tornadoes or hurricanes or any other type of natural disaster that you need to respond to? And then with the health, we're looking a lot about the indoor air quality, the indoor environmental quality of the building. And then the decarbonization is specifically that electrification, community solar, low embodied carbon, microgrid type stuff. How can we expand that further? So that entire bit of that vision needs to fit within a quality assurance program. And that to me, I think is one of the highlight of what we've done so far, where we have not just the good building science and modeling and design behind it, but then is that building getting built to that design and meeting our standard correctly? And when you submit a project for review, this is a question we get a lot, like, why would I even pay the extra money to have the project reviewed? It's another level of quality assurance. for us to take a look at it as third-party reviewers. So this is all going to be built around the ASHRAE Guideline 0.2 framework. So that's about planning and programming, assessing, investigating, designing, implementing that verification, and the operate and continuous maintenance. For the decarbonization, the idea we have is to put whatever our design is through an entire life cycle cost analysis with an artificial cost of carbon built into it. And that's what helps. That is not necessarily the metric of what you're building to, but it's a tool to try and figure out where that sweet spot of building retrofits and upgrades are headed. So to account for that life cycle cost analysis, our current term for it is a current moniker for it is ADORB. That's the annualized decarbonization of retrofitted building cost. And it's a summation annualized of direct energy costs. So what are you paying to your utilities? The direct retrofit measure costs. So what's your final bill to the construction company or the contractor who's doing the retrofit? The cost of carbon, including the upfront carbon. So what's the embodied carbon in the construction process and in the materials that are being added for the retrofit. And then the cost of the operational carbon. So any emissions that are happening from either the grid or on site. And then a cost of the energy system transition costs as a means of regulating peak loads. When you electrify, and if we electrified unretrofitted buildings right now, we'd see a significant increase in peak load on the grid. And this cost here is meant to drive that towards lowering that peak design load.
Al, before you this slide, I got a question for you. So when I think of decarbonization, I think of it meaning I'm replacing my fossil fuel burning equipment with electrical equipment, and maybe I'm adding solar to offset some of that. But this is, you're sort of expanding the term decarbonization to mean other things here. Is that kind of how we think about this?
Yeah. So it's the total life cycle and carbon intensity of the building itself. So one of the costs that's in here is that cost of embodied carbon. So by accounting for that, we can encourage smarter design decisions towards low carbon insulation materials if that's a possibility for the retrofit. And then you're right, like the electrification and either solar offsetting, or even if you're just on the grid, we're looking at a projected decarbonization flight path on the grid localized. So different areas of the country also have different grid intensities, and we're accounting for that. So if you're in the Pacific Northwest, you might be able to do a little bit less with your envelope to hit that resilience metric, and then you can just electrify from there. If you're here in the Midwest, or if you're out in the Northeast where a lot of our generation is still fairly carbon intensive, you'll need to upgrade the envelope to that, but you might also see more payback by putting in a little more embodied carbon into the building and then electrifying at a smaller scale.
Gotcha.
So resilience, again, we're looking primarily at thermal resilience, but all the other resilience elements play important roles in here. And it's either at like a building, a campus, or a block scale. So there is an opportunity for passive resilience and maybe some mixed mode operations going forward. And currently looking at the small building and single family scale.
Sorry,
yeah.
Al, what do you mean by mixed mode?
Yeah, so ultimately, like true thermal resilience of a building would be the ability for that building to float based on or like a truly passive survivability type thermal resilience, like thinking of like the work of Alex Wilson at the Resilient Building Institute. He talks about if there was no power supplied to the building and everything was cut off, how would that building float in temperature during typically an extreme weather event? There's a report from the National Renewable Energy Lab that came out in December 2022. You can find it on the ResStock page that deals a lot with the coincident occurrences between extreme weather events. So the cold snap in Texas that we had 2 years ago, the Pacific heat dome in the Northwest, and power outages. So that's the idea of the thermal resilience is just the building is a thermos keeping you warm throughout time or keeping you cold during a cooling outage. And then on the mixed mode situation is we might need to actually run a few mechanical systems to make that work. For example, I've done some simulations where we looked at passive survivability and just modulating an operable window to try and provide adequate ventilation to prevent the occupants from asphyxiating in a very airtight passive building. But that doesn't quite work because now you have no heat recovery on that. But an ERV running at about 5 CFM a person is a fairly small wattage, and you could run that off of a battery or a solar system. And then in the summertime as well, especially in a climate like Chicago, where you've got hot, humid summers, it's almost impossible with our current technology to passively dehumidify a space. And that tends to drive up the thermal discomfort and that heat index that makes it harder for humans to sweat. And that's the concern we have there. So in the summertime, you might need to play in with some kind of natural ventilation and night flush mode, but run a little bit of battery or PV operated dehumidification during the day. So it doesn't just have to be the building envelope alone doing the thermal resilience.
Thanks.
Sure. So as part of this research, we're trying to develop a modeling protocol and a piece of software to support that. Looking at 7-day outages in the extreme weather events that are built into a lot of our typical weather files. Also looking at potentially shifting that to make sure we're encompassing what the realities of a future climate could be. That's a spot that I've been stuck in because we don't really have a lot of good future extreme weather data that we're looking for yet. There are a lot of people working on it, but just no results out there for us to use. Maybe there's like I said, there's on-site PV and batteries to provide limited power for refrigeration, for keeping food safe, and an ERV or some combination like that. We're assuming people are there consistently during this outage situation. You're not going to leave out into the middle of the polar vortex when you have no means of power or anything like that, and then reducing ventilation rates from standard design just to mitigate carbon dioxide buildup. And all of that responds to we want 0 hours in the space below 35 degrees Fahrenheit, it's 2 degrees Celsius, as a means to prevent freezing and damage to building infrastructure. And then we're trying to limit the set hours, which is a thermal comfort metric that we're using as an analog for hypothermia. And then in the summertime, because we see extremes in both hot and cold happening and potentially increasing as well, our summer criteria remains the same, but maybe there needs to be a little bit more mixed mode like we were talking about earlier. And we want 0 hours in the danger zone of the heat index and a limited amount of hours in extreme caution. So again, not quite comfortable conditions, but survivable conditions that build in value to the occupants. There's all those health hazards that I had mentioned happening, and the EPA lists a long list of these hazards that they identify as risky to building occupants. And then FEMA is the one that's going to cover more of the rest of that resilience. So seismic flood, hail, wind, snow load, and wildfire. So responding to all of these concerns as well should happen in a retrofit process. So the requirements of the standard then, in a typical Phius fashion, they're not super hard and fast requirements, but there are prescriptive requirements. There are the modeling backstops, which most people would recognize as the heating and cooling load limits and heating and cooling demand limits. This is a little bit of a different type of standard. So Buildings should be resilient and be able to respond to that. And then we need to make sure that we fix any of the existing deficiencies that pose a risk to indoor air quality. This entire thing is wrapped in that quality assurance process. And then trying to make sure we even need to retrofit the building. If the building's in a spot that is in a floodplain and it's flooded many times and it doesn't make any sense to try and put it on stilts, maybe we don't retrofit that building, because there's a lot of other ones that probably should be. And then that project cost data is measured in the energy report. So that's all the quality assurance requirements that get built in. And then to try and decide between the multiple options you have is where that life cycle cost of carbon comes in. So also, we're writing this as a potentially open standard, so that sort of like an ASHRAE standard or an ANSI standard would be, so that jurisdictions could adopt this as potentially a building code, or it's usable by other people and not just by us. But Phius would continue to maintain and service the standard, as well as all of the current people that exist within the Phius ecosystem would have similar functions that they currently perform. This is a little bit more detailed on that quality assurance process. For the sake of time, we're going to skip it. And then also the owner, it still is the owner's project. So they're welcome. If part of their retrofit is a new kitchen, that should be included in there and should be included in the process. Some of the, in addition to like functional requirements. So if they need an ADA door, or if they have preferred vendors, so like they have a cousin that does windows or something, that could help out. So to support all of this, we've been working on developing a new modeling tool that eventually will probably get built into one of the new versions of Woofy, or exist as an open source modeling tool that people can use. And it does that hourly resilience simulation. It does an hourly annual simulation based on normal building operations. And it does that entire life cycle analysis, including the cost of carbon, all built into it. Right now, it's not really usable by humans because it's mostly code, but I'm working on developing a fairly simple GUI interface to link in input files. So I've done a little bit of testing on this, and Tom's very kindly provided me a couple case studies that I'm going to be working on, and I've already broken this some of the elements of the software. I need to add to it to make it work out correctly. But so far, I've pumped through the DOE prototypical single family house. This is what P&L uses to test all of our residential codes. It's a 2,200 square foot, 3-bed, 2-story, just blocky, detached residential house. And because part of this research was done with RMI and the DOE and all that in the Advanced Building Construction Collaborative ecosystem, they like to work in packages. So we had tested a couple different packages, this baseline house, which is what we'd find in a typical existing house, an just flat out electrified case, the market ready envelope, which is an inch of foam, a little insulation in the attic, a tiny bit of air sealing, some low E storm windows. Then IECC 2021, just retrofit the house to modern code. The IECC 2021 with the passive house level of air tightness, and then just flat out Phius. And as I mentioned before on the modes for the summer, we've looked at a couple different modes here. And ultimately, this is a sort of a game between, if you can't do it with natural ventilation or a night flush or some kind of thermal mass and combined strategy like that, that's where you end up in the mixed mode thing, and you're trying to size batteries and PV adequate to run a heat pump during an outage if you had to, on a setback, that is. So, I've done a couple cases here just to show this base house that's just been electrified. So what some people would consider an effectively decarbonized house. This is 0 degrees Celsius, 32 Fahrenheit, and the house dips below freezing after about 3 days in an outage here in Chicago, even with the occupants and the refrigerator as the internal heat gains in the space. By doing the DOE ready envelope, this is the 1 inch of foam and a little bit of insulation in the attic. We're able to get maybe about 4 days into there before we dip below freezing. in the space. And then get out of here, Zoom. With the IECC and the IECC, we can make it about 5 days. And then with the IECC, with the Phius level of air sealing, we can keep it out of freezing. So as we make all these little incremental improvements to the building, and we're trying to figure out what that sweet spot is for that heating outage thermal resilience, I think that's really going to end up driving the insulation and the air sealing required for the building envelope. The full-on Phius retrofit never gets colder, dips a little bit below 10 degrees Celsius, so it's about 50 degrees Fahrenheit. So not super comfortable. I mean, I'd like 68 or 70 in my house in the winter, but a much more survivable situation if we ever were put into that scenario. Looking at the cooling, this game gets a little bit trickier, mostly driven by the humidity here in Chicago. If you just let the house sit and float and try and ride it out, it can get quite warm in there, and we do have a lot of time in uncomfortable periods, but we're able to stave off that peak 103 degree day built into our standard weather file. A little bit more insulation and you can pull that peaks down, right? The Yeti cooler works as it does because it's well insulated and well air sealed, so improving that will keep the cool in the space. Between the market ready envelope and the IECC, there's not a lot of change. Once you go towards the Phius retrofit case, we're actually able to keep the cool within the space and ride it out and stay under 30 degrees Celsius in the space, which is, again, just that cooler effect working to your advantage. The one other thing to note, though, when you do go to a more air-sealed option beyond this, is you have a hard time shedding a lot of that humidity in the space. So while the dry bulb temperature might be cooler, this is where you might need some kind of dehumidification or some other means of cooling down occupants, because you can't really sweat well in 100% humidity. Real quick, I know I don't want to encroach on Tom's time too much, but we looked at a couple different cases here of the natural gas only retrofits and then fully electrified retrofits and their total adorb cost, with some estimated embodied carbon, and everything else was calculated through our current version of the software. And our most efficient, lowest life cycle cost is still that full-on passive house retrofit, but some of these other ones that hit the thermal resilience metrics, like this IECC 2021, in air sealed to Phius electrified, is still much lower than that initial baseline. And we are seeing a little higher cost just going straight to electrification. So it's easier to push people towards electrification if you are doing envelope upgrades as well, because you are going to save on that. You actually are going to start seeing savings on that utility cost. Slightly warmer climate, New York City, a little bit easier. It's a little more mild there within the confines of the current adorb. And then in Nashville, which again is a little bit more mild, you don't need as much embodied carbon. You don't end up spending as much on space conditioning as you would here. It's a little bit of a lower life cycle cost as well. So thank you. I'm happy to have I want to give Tom a chance to present, but then we can have more discussions and questions further. And then the shameless plug for PhiusCon, come and hang out with me in this lazy river in the shape of the state of Texas next November. So thank you.
Oh man, you sold it. Thank you, Al. I tell you, I am partly responsible for instigating this work, because when I started working on my own house a couple of years ago, I got a little concerned that, there's no way, because of things that I had done in the house, that I would be able to make Phius metrics as they stood. And I said, hey guys, if you don't figure out a way to do this, we're not going to be part of this movement, which has got to be a movement. And I just don't know of any other standard out there that really has sort of third-party quality assurance to help people if they have questions about what's the right way to do this. So little that I know, the big brains of Al and Graham would be like doing this deep of a dive. So anyway, that's where we are now. So all right, I'm going to show some case studies here, but before I do, so this is just a image of a lot of our Phius buildings or DOE Zero Energy Ready projects that we've done over the last, well, since 2011, really, when we really started hitting our stride. There's about 10 more that we have in progress that are like decarbonizations or Phius retrofits that we don't even have on here yet. And they're full Phius retrofits, a couple here in Oak Park, which we're going to do some tours of later in the summer. We'll announce that. But we've been coming from on this, I think a lot of people think about retrofits, it's kind of embodied on this slide here, which is that, we were looking at this Frank Lloyd Wright building, which we'll be showing here in a minute, and thinking about how much energy used operationally versus its embodied energy. And so if you look at this graph, the orange line going up is the operational energy that it's using right now that we modeled in Woofy Bassett. And then you see that it starts there at 4 million or 40 million, whatever that is. And that's just BTUs per square foot, how much embodied energy is in the building. So we started asking ourselves, all right, what if we tore it down and did a new passive house? I mean, not really, but just like a what if, okay? So that would use a whole bunch more energy, and it would, recapture that carbon expenditure in like 12 years. So we're talking about going to 2030 something, 2035, right? And we're trying to get to like zero carbon 2030 ideally, right? So it's like, well, this isn't a good idea. And then like on the opposite end, what if we just did low hanging fruit, just, blew some cellulose in the walls and did a little bit of air sealing, easy to get stuff. And that's that green line. And we're like, wow, well, that actually, let's use that as a baseline to compare against. And so, you can see like if you just did low hanging fruit and you try to justify like tearing a house down for energy reasons and building a new one, you're 17, 18, you're in 2040 before you're recapturing the energy. So the idea is we gotta retrofit now in cold climates the buildings that we can. We have to do a small amount of energy. You have to use a small amount of energy to do it, or else we're spending energy to save the energy problem. So a year or two ago on the Greenbelt Home Tour, we put this thing together to sort of imagine what we think of as an idealized scenario if you're going to decarbonize your house and retrofit it, remake it for an old house for the next century, let's say. And so the idea was, well, start with the envelope, ideally the roof first, and then the walls and floors, and I'll talk about why in a minute. And then look at the basement, then take care of the mechanicals, the HVAC, get to efficient like heat pump based systems, and then take care of your remaining appliances, change your gas cooking to induction, etc., and then put solar on, and you're done. And so that's kind of the idealized situations. And what we realize in doing some different projects is that there are limiting factors and there are enabling factors. And the limiting factors that we really hit up against are, first of all, people living there. You can't do a gut rehab unless people move out or haven't moved in yet. So, that's big. Historic preservation is another one that we keep running into. And while it's fun to just sort of throw barbs at preservation, I mean, there is some value in culture and so in beauty in buildings. I mean, that Frank Lloyd Wright building to me is close to my heart. I wouldn't dream of covering it up with with insulation, or tearing it apart. So so that's one. And then of course cost. I mean, it's expensive to totally reclad or gut rehab a house or a building. But there's the flip side of that, which is the enabling factors, and end of service life of a surface or equipment is one of those. So like for me, my siding, my asbestos siding was starting to flake off. So I had to do something about that. And so when I do something about that, I can go and like slap some vinyl over it and pretend it's not a problem, or I can take it off. And if I take it off, then I have the chance to insulate. So anyway, so there's opportunities there, which yes, they're going to cost some money, but they should be looked at. And certainly, yeah, if your water heater goes out, put in a heat pump water heater. And so that means you have to plan for that, because they don't necessarily have them just right on the shelf at Home Depot, or maybe they do, I don't know. Change of ownership is an enabling factor, because if people are moving in, they can wait a few more months and do a little more work, maybe. I think the incentives that we're starting to see through IRA and CEJA are starting to enable some more of this work. But the biggest one that we've seen in these examples that we're going to show is really coming out of a desire for people to have a building that aligns with how they think a building should be. I mean, and so this is where the car analogy is good. You know, I think people like their electric car, not just because it's cleaner, especially if they have solar, but also because it feels like a smarter way to drive. And so there's a lot of that going on with our example projects that are sort of like trying to get the zeitgeist going in the building. And a lot of times we're working on buildings that are 100 years old. So, but zooming out big picture again, I just wanted to mention a couple articles I've read recently. So if you're not on Green Building Advisor, it's a good thing. It's been really good for me to see a lot of heat pump articles and whatnot. But you know, Martin Holliday, that I'm sure everybody knows, he's a great skeptic and clear-eyed thinker, and he did a review of Bruce King and Chris Magwood's recent book, Build Beyond Zero. And these guys are the kings of carbon. I mean, they've literally written books on it, and a software tool, the Beam tool for embodied carbon. So these guys really know, and they have all these ideas about, you know, how to do it. And of course, Martin's sobering assessment was, for these solutions to be effective, they have to be implemented now. And a lot of these materials aren't even developed yet or not being mass produced. So there's definitely a need to really think hard about carbon and how we solve these things as we go. But don't let the perfect be the enemy of the good. Go do your best, right? The other thing is this article that I just saw today, and Rachel White published it April 7th. So it's recent. Do deep energy retrofits make sense? And so this one, go and read it. I think it's really cool. She's basically saying what Al is saying, that you don't need to, you know, don't spend a ton of energy in the form of insulation and other equipment if you can do a minimal amount and hit this resilience. Maybe you need a little larger heat pump system and some more solar, but that's a good way to get there. Okay. What time is it? 5:38. Oh, geez. Al, you took too long. Sorry. Okay, I'm going to run through these and not give Al a hard time. So these are the 5 different ones. I'm going to dive right in and say our goals on these. First of all, was dealing with deferred maintenance or end-of-life equipment and services, real deficiencies, dealing with deficiencies, like on my house with the siding. We went into it with a Phius mindset. We want to insulate for energy savings and resilience. We want to air tighten it for durability and health. We want to decarbonize, so take out all the gas and go to all electric using the efficient sources, you know, heat pumps. We're going to plan for or go ahead and incorporate solar PV. And we're going to shoot. My thing at my house is like, well, if I can't make all the Phius metrics, maybe I can make the source energy limit at the worst. So that's kind of our baseline list. Make sure we do that sort of fair share energy. And I found that I could with modest insulation upgrades. So so in doing this, we feel like these houses are relevant. They make sense, today. We wound up reducing overall energy use 70 to 100% on these houses. So so I'm going to start with my house here in a little more detail, and then we're going to go a little quicker on the other ones. This is the condition that I found my house. When you look at this section here with the red arrows, showing where moisture is coming in through the slab with capillary action. There were no capillary breaks before, what, about the 1940s or so. Moisture and cold is coming into my foundation. Air is moving up through my walls, which are actually not double top plates. They're mostly balloon framed. And then air is moving up into the attic. So it's doing the whole stack effect, all that stuff, giving me an EUI of about 115. I had about 10 ACH50 for blower door test. So it's leaking like a sieve. Had an old gas furnace. Only ventilation I had was a kitchen hood. And the exterior was in disrepair. So it was a really good retrofit, exterior retrofit candidate. So we lived in the house through this. But I had done two things before I had thought about this, before I knew about Phius, you know, back when I was young and dumb or dumber. I had replaced the windows because my son's lead count when he was a little young guy, 18 months, went up because of the windows going up and down, his mouth at windowsill level. I just ripped them out and put in new double hungs. So they're double glazed. They're not very airtight, but they still have another at least 5-10 years in them. I'm sure 10, probably 10. So I'm not going to rip them out and spend a bunch of money and throw away that carbon. So I was like, well, I'm not going to be able to make Phius with these windows. So, oh well. And that's kind of how this whole thing started. So yeah, I want to show the energy modeling here because to me it was really eye-opening. And we kind of created this little like speedometer dial to show the EUI, so energy use intensity, that's kilobTUs per square foot. It's like a miles per gallon for the house, right? And I'm also tracking here like my furnace size. Energy modeling shows I need like 100,000 BTU. So for this little story-and-a-half bungalow, I need like a little over 8 tons of heating. And that's why in this graph, the big red bar is like heating, right? This little picture down here in the lower corner is the old coal chute that somebody filled up with bricks next to the old stand for the gas meter. And this was like the day they took it off. So I had to take a picture of that. And so we were stripping off the siding. So anyway, that's like two old technologies gone. So first thing I did on the house, and this is before I knew about Phius and all that, or actually I didn't know about Phius, but I didn't have a lot of space and whatever. I did open cell foam up there. So I got a decent improvement on the air tightness and cut the energy down from a 113 EUI down to 77. So took care of the roof first. It's only like an R26, so it's not a lot, but it's decent. It was about as decent as I could get without losing my headroom, I'll put it that way. So then when I really got into the project, the meat of the project a couple of years ago, it was starting with the wall. So we hired the asbestos people to come and take off the siding and stripped it down to the old sheathing so we could put this Henry blueskin on, because the real big opportunity here is to address the air tightness. And get a vapor control, an air barrier rather, on the outside of the building. So the blueskin is a peel and stick membrane that's airtight. And so that went on over my old sheathing. And then over that, we put a couple inches of Styco wood fiberboard as our exterior continuous insulation. It's a beautiful material because it's carbon negative. So it's a carbon sequestering product. And then you can see on that picture the little white tape squares. That's where we cut holes to blow cellulose into the wall. So that's another carbon sequestering product. So we blew cellulose in the walls. We put Styco over it, and then we put new siding on it. So here my EUI is down to 38. I mean, so there was a huge opportunity in the walls because they were super leaky. And they were uninsulated. So it's only like an R20, so nowhere near what we would do, about half of what we would do for passive house. But look at my red heating bars going way down, and look at my furnace size. It's gone from 100,000 BTUs down to 26. So it's like, wow, I need a much smaller heating plant now. So that's kind of the big idea. The basement, you can see I go from 26,000 BTU hour furnace down to only 22.6. So there's not a lot in the basement in terms of peak load and I'm going from a EUI of what 38 down to 31. So you're losing energy out of your basement, but that wasn't really the driver here. It's not a huge piece of the pie, but all the moisture is coming up, all the radon is coming up, and there's some heat loss. And so it's like, I can't have a nice, dry, comfortable house with a wet basement with centipedes crawling around in it. So anyway, we went ahead and did it. There's a carbon cost to concrete, no doubt, and it's high, but I didn't see another way. So the basement got done like that. We wrapped this InsoFast as the foam that we wrapped up the inside of the foundation walls. And boy, is it nice now. So anyway, down at 31, and then we replaced the mechanical systems. Now, I want to go back and show underneath the graph, you can see my annual energy cost if I'm running gas in this house. After I've done all the installation, is about $1,100 because my loads are low, right? And then I go and switch out the heat pumps, and my energy cost is almost $1,700 because electricity is still more expensive than gas. So some people need to know, they're just going to unplug their gas and plug in electric. Even with efficient heat pumps, you're going to be paying more for your energy to heat. So the more you can insulate, the better you'll be. But then when you go to the next stage, which is putting on solar, then it's down, here's $990. I cut it in half. And actually, I added another 12 panels. So my annual energy cost is about $0. So, $14 a month for my ComEd service. But that was, yeah. So anyway, with the switch out on the fuels, my EUI goes from 31 down to 19. So it's a big deal energy wise. And that's basically a mini split or a split system for heating and cooling, a heat pump water heater, and I did an ERV. I got the serve. So anyway, that was like the steps going all the way through. And this is kind of what the section looks like now. So I have continuous insulation. I've got capillary breaks, and it's way more comfortable. And I'm dying to hear what Al gets with the thermal resilience. So I got my ACH 50, my air tightness down to about 2. So I don't have that in the new terms, but that was how ComEd needed to see it. So a passive house of this size would be about 1 or maybe 0.9. So it's pretty darn good. A hell lot better than 10 where I started. And it looks better. I hope you think so. Okay, let's talk about Frank Lloyd Wright. This guy had about the same leakiness as mine. This is the Oscar Balch House, 1909. It had an addition put on in the late 20th century. And it was all run by gas, with space pack in the roof joist, no insulation up in the roof. The roof was an air exchange mechanism. It was basically like the ERV of the house without the R. It's like, yeah, so basically just leaking like crazy. It's a rubble wall foundation, sucking moisture up. So this was something we had to be sensitive with historic. So we didn't get much in the walls. We basically knew that we wanted to recoat the stucco, which hasn't been done yet. So because we're recoating the stucco, we felt we could drill the outside, put cellulose in the walls, and then when we recoat the stucco, it can be seamless. For the interior of the basement, we didn't feel that the concrete slab was historic contributing. So we said, let's take it up, put down insulation, capillary break, and then get our moisture control down there. With the insulation, we did a dimpled membrane against the rubble wall to create a capillary break. And then mineral wool, you can just do spray foam otherwise, but spray foam is not reversible. And reversibility is a principle of historic preservation that you want to be able to take it off so you can see what the house was, the building was. Now, reversibility didn't enter into it on the roof. We did spray foam up there. And spray foam we really are cautious about because it's very carbon intensive. We only use HFO blown closed cell. Make sure you do that. You can still get HFC blowing agents here, which are hundreds of times more global warming potential than than HFO. So if you are doing any spray foam, be certain it's that. You have to get a submittal from your insulation contractor. We did that on our house, and he's like, no, we don't have it. So we had to hire another person who did. So anyway, just enough closed cell to get our vapor control and our condensation control, rather, a couple inches. And then what Rachel White was saying in her article is then fill with cellulose. Here we couldn't fill with cellulose, so we did open cell foam. But yeah, the ceilings were in disrepair in this house. So that was one of the things. It was an opportunity. Take the ceilings down, spray it, put it back up. So yeah, we cut the energy loss down, or the heating load down massively. And then we just offset the energy by getting solar on the roof. It's a flat roof, can't see it from the street, so it's historically passes muster. A very different kind of attitude of building here, this Chicago bungalow, which is in construction right now up on the north side. We are taking sort of the minimal foam approach, using a lot of cellulose on the interior, which of course is a concern from a building science standpoint, because brick is a sponge and it's sucking up moisture. And so we worked with 475 Supply to get a package where we're spraying air and water barrier called Viscon on the interior face of the brick. It's this kind of, it's like a fluid applied air and water barrier. And then for the part that goes below grade, we're using dimpled membrane that connects to the interior perimeter drain that you can see there in the building section. And then up above for the brick and the roof, because we didn't have a lot of room to fur down that ceiling and keep the bedrooms that are there, we're using the HFO blown foam. So we get about 5 or so inches or 7 or so inches up there. Again, these are relatively modest by new passive house standards, but we're getting the heating load down in this house down to 2 tons. So a small ducted mini split in the basement with a small cassette in the second floor, and we're set. We have an ERV that's dealing with the fresh air there, just a renew air that's sort of piped into those systems. So it's not going for passive house per se, but I think this one probably would pass the resilience test. I'd be really interested to see. So that's our brick bungalow. New EUI of 12 without the PV. So when PV goes on here, we could get to 0 pretty darn easily. This is a Chicago 2 flat. The owners needed to gut rehab it. And so we basically came in with a kind of a flash and bat type approach, closed cell foam around the entire perimeter, and then enough for condensation control at the walls, and then cellulose inside of that. So again, the brick's a sponge, it's sucking in the moisture, so you got to keep it out. And this one, same thing, here we are getting down to just over 2 tons for this 2 flat with a newly dug out basement, and a nice new big family house here. So I gotta keep moving along because it's, oh gosh, only 7 minutes. Final one here is a house built in 2000. The siding was wearing out. Woodpeckers were taking it apart. And so we did basically the same retrofit as we did on my house, wrapping it with, stripping it down, wrapping it with blue skin, and putting on the Styco. Now the Styco is very vapor open, as is the blue skin. And that's important because this, house built in 2000, we opened up a wall to see, but this was craft face bats, and that's a vapor, vapor control, basically. Some houses of this era, you might see visqueen, so you don't want to create that vapor sandwich when you want to put like polyiso or a vapor closed insulation on the outside. Plus, who can argue with this Styco with its, negative embodied carbon. Really interesting detail at the roof, at the attic, this, big, huge framed attic with several hips and dormers and all that typical McMansion-y stuff. So the idea there was like, we just put furring strips on top of the ceiling joists, so we could bridge over all the conduits and stuff that were running there. and then we taped that plywood, and we put plywood on top of the furring strips and taped it, and that's our or air control at the top of the house. But we couldn't get that all the way to the edge because of all the rafters coming down. So we just did a little bit of closed cell there to make that transition, and we got air tightness of ACH 50 of 1.09. So really impressive air tightness. Eric Barton, the builder, just knocked it out. We did new triple glazed windows throughout because the windows were already at the end of their service life. So yeah, we got down, below 3 tons of heating and cooling here, new heat pumps, new solar. We're almost at net zero with this house. So not Phius, but getting to zero. I'm going to pass over the sort of deep thoughts here. Come back to one of them in a second, but I want to open it up for questions first. And I want to get to this slide, which has got your self-report code for the CEU credits. So I have a couple of thoughts to throw at you if we have time, but let's open it up for questions first if we could. I see there's a chat here. Let me open the chat. How much did the retrofits cost? Okay, I'm going to jump to the first one because cost is a huge thing. All right, Bill Lyons, Bill from Elevate. If it's People's Gas fixed charge is $600 a year. Yeah, so that is a big thing. I will say that the Nicor charged me $1,500 to take my meter out, and they didn't tell me before they came. They just showed up one day and took out my gas. I'm not ready. It was already gone at that point by the time I got home. But anyway, just kind of hilarious. So yeah, there is that kind of sticker shock. You can buy a lot electric with $600. It's true. Efficient house is better off with electricity, definitely. Did you test the moisture permeability of the brick before adding interior insulation? So this is a question about the brick retrofit. What about how do you assess whether it's going to be safe to put interior insulation on? The Phius Alliance, we had Bill Rose and Paul of Domus, Paul Knight, talked to us years ago about this issue, and also Joe Stiebrick did a talk to Phius Alliance. And the general thinking is, without testing, you're probably going to be okay if you have good bulk water management. But that's not enough. And so I talked to Coda at Building Science Corp. I hired Building Science Corp to just kind of bounce ideas off them. So I'm not saying that they are responsible for this design. I am, but basically the idea was any place where moisture can sit and get into your building, you got to deal with that. So his high-tech way of doing that is taking an old ketchup bottle and putting water in it and pouring it on a sill and seeing if when it drips off the sill, it goes back and hits the brick or it goes down. And if it doesn't, if it goes back and hits the brick, well, you better cut a kerf in there or put a flashing in there. So it's basically like every little place like that you got to deal with. Now our house had really good overhangs, and so we weren't taking out a lot of moisture. There is one place we're getting efflorescence that we can't figure out, and so we haven't insulated that yet. But basically, the moisture permeability, you can test it. It's expensive, and it probably wouldn't change what we did. So there's the more insulation you add, the more risk there can be. But yeah, because these buildings used to stay dry by just blowing energy through the walls, and so that is definitely like the building science fundamental of all of these projects is how is it going to behave now that it's not being dried out from the inside. So yeah, that's I think a whole other program in its own right. But we definitely go to Building Science Corp for these kind of things, for the papers that they've published and all that. Okay, how much did these cost, and how much would it have cost to build a Phius house from scratch? So like for my house, I spent probably close to $175,000. A lot of that was maintenance stuff that needed to happen. If I were to do a new house, there would have been at least $700,000. So a new house is, you have to do everything. You can't stop part way. But with a retrofit, and this is something that Al didn't mention, but you can phase it, and you can keep all the things that are good and some of the things that are decent, and you can, scale it. So like when these people were gutting the 2-flat, they didn't say we wanted a Phius retrofit or we wanted a super energy efficient retrofit. I said, you're gutting, you should insulate, it'll save you money. And they're like, yeah, that makes a lot of sense. So it's actually, nobody did an ROI calculation on that. In a lot of ways, I guess we're thinking it's dumb not to, so what's the right thing to do? So anyway, how much do they cost? The cost goes all over the map on these. So it's there's no like cost per square foot we can throw at it, but I'm telling people what I paid for mine. I haven't broken it out in terms of how much was deferred maintenance and how much was stuff that I wanted. I mean, some of this honestly was me wanting to live with, well, first of all, a house I really felt good about, but also the technologies that we design for a lot of people's houses, just to know how it works and understand it through experiencing it. All right, question for you, Al. Looks like the 5 Adorb categories for cost apply to new construction as well as retrofits.
Yeah, so the initial intention of it was just for this retrofit case scenario to help select between those different options. But there is the thought as well that we might roll it into a new standard tool at some point in time. And that's what Graham calls FCalc or something like that. And could you run through the energy? Yeah, so the energy system transition cost, it's probably about the smallest part of the entire package of the life cycle cost, but that's the cost to society essentially that you have to pay for the additional grid capacity that you're creating the demand for by electrifying with non-carbon intensive power generation sources. So if I'm going to add an additional 5 kilowatts of peak load to the grid, I'm essentially paying for that 5 kilowatts of solar panels that are being installed somewhere in our electrical system. It's very small.
So Al, on that,
Yeah.
it is the peak load. So if we start to get past net metering as California has, and we're really driving self-consumption, battery, all of that, does that eliminate that factor in the adsorb? If
Yes.
Looking
Yeah,
a couple years ahead when we start to look at power and needing to have batteries so that you can chop that peak load, it would take care of that.
Yeah, essentially I'm monitoring the Energy Plus. It's the variable that describes the electricity purchased from the grid, and I'm monitoring that hourly and finding the max moment of that. So that's whatever the peak demand from the grid is. So if you have on-site solar and battery, and even though your actual peak load of the building is 5 kilowatts, but because of that your peak load is only 1 kilowatt on the grid, you'd only pay for that 1 kilowatt in the adorb cost. And again, this is not a real fee that anyone is being charged. It's a decision-making tool.
It is a fee.
This time, yeah.
It is a fee if you're on hourly pricing.
If you're on hourly pricing, yes, yeah, it'll definitely help you sort through that. If you have that, because I don't know, does ComEd have that build? Do you know off the top of your head?
Yeah, they do.
Okay.
They have hourly pricing, and one of the fears is with electrification, you can get hit with a peak that can tank your savings.
Got it.
Because it affects your yearly rate.
Yep.
Yeah, for sure. All right. Well, thanks everybody. And hey, Laura, I see you just showed up on the camera. Good to see you. So, all right. Yeah, well, it's a little after 6. If there aren't any other questions, we'll hopefully see you all next month. But if there are questions, feel free to email and through Pass Alliance or post on the meetup page. We have a discussion group there, so whatever works. Oh, okay, she's been there. Good. All right, I just didn't see you. All right, thanks everybody. Anything else, Jennifer? All right, thanks everybody.
Bye all.
Good night.
You.
Thank you.